the one that's assigned this week that's due by the end of next week. And this is the one that's using the rotary encoder to measure convert radial displacement to linear displacement. So rotational displacement, or how far you turn the knob into a straight line. And the reason you'd want to do this is depending on the type of circuit that the encoder is feeding into. Typically, it would be an analog to digital converter. So then at different phases, you would get different outputs. Washing machine functions. I'd say like older microwaves that had the turn knobs on them. So in this one, our key points are coming from the table, data, and your percent differences. So your data collection and analysis are combined in one part here for 40 points. You don't have to answer the questions, but you don't get those 10 points. So a picture for 10, a table for 40, and a couple of questions for another 10. And again, I would walk you through these labs, but that's what the videos in the course shall do. So I think that's kind of why they put them out there, so that I don't have to do stuff like that, and I'm really impressed because they did a good job.
Course project, you will need your mega board, the USB cable, your rotary encoder, male to female jumper wires, a round object to attach to the rotary encoder, and a tape measure, meter stick, or a ruler. Now, to begin, what we're going to do, notice we don't have the breadboard. We're just going to directly attach our rotary encoder with our mega board. So notice there's 5 pins. We have the ground, the power, the switch, the data, and the clock. Now, the data and the clock work in conjunction with one another to determine the on and off period of the sine wave. The switch, on the other hand, determines whether the rotary encoder gets pressed in. So we're not going to be connecting that. We will be, however, connecting the plus and the ground. So let's go ahead and start wiring it up. So let's begin by connecting the ground to the ground on the mega board. Next, we're going to take the power and connect it to the 5 volts on our mega board. Next, we're going to take the clock pin and connect it to pin 8 on the mega board. Now the clock is all the way at the top here. Finally, we're going to take pin number 7 and connect it to the data on the rotary encoder. Now you're going to go ahead and attach a round object onto the shaft of the rotary encoder. You want to make sure that it's secure in there. Now I'm using a ball that I was able to drill a hole into. However, if you don't have a ball, you can use a cork or you can use a bottle cap. Now another thing you want to keep in mind is the traction that's going to be in between your rotating object and the surface at which you're going to be rotating as well. So notice with this particular object, this plastic ball that I have, it doesn't really rotate well on this table. So I need to have something that's going to generate more fraction. So what I'm going to do is take a foam mat. And this foam mat, you can see, creates enough traction to rotate. Now you probably want to practice a few times to make sure you get good, consistent rotations. All right. Now another thing you want to take into consideration is the number of pulses that are in this particular rotary encoder to complete one revolution. Now I've mentioned in the documentation that it is 40 pulses, but one thing you can do is make a little mark, attach it, and then you can just rotate, and you can then see to make sure that, yes, indeed, once you get back to the same spot, that it is indeed 40 pulses. So check that out and make sure you have a good understanding of how this sensor works. So now it's time for us to take our experimental configuration, upload the code, and collect data. So now that I've uploaded my code, what I'm going to do is, well, I'm going to measure the distance which I'm going to travel. So I see here we have 41 centimeters. So that's what I'm going to use to compare. Because remember, what we're doing here is we're converting radial distance to linear distance. So you want to begin at one end and just start rotating. Notice the number of pulses that are in your serial monitor as you're rotating. So you're going from start to end, and you want to end where the shaft is, so from the point that you measure. So that will be your complete revolutions, and you want to denote the number of pulses. Now you want to complete this experiment a couple more times, have some more trials, and determine the precision of your experiment.
Once your code has been uploaded onto the microprocessor, go ahead and open up your serial monitor. Begin to rotate the object in one direction, then in the opposite direction, and you'll see that the numbers are decreasing. Bring it back to the 0 position and start rolling. All right. Now I'm going to go ahead and use a ruler to measure this distance as well and compare it with what I'm going to convert this radial distance into linear distance. In my PowerPoint deliverable, I'll be using the table that's in here to collect all my data. You could also use the one that is in your guide as well. So my object has a diameter of 4 centimeters or a radius of 2 centimeters. The number of pulses that I had was negative 87, but I'm just going to include the magnitude of that. Now I need to compute the theta, so it's the radial distance that it traveled. And to do that, we're going to use the equation that was provided in your guide, which is 1 over 40 times 2 pi radians times 87 pulses. And here I have 13.66 radians. And here I have 13.
I'm going to come back and freeze frame that one because that's the part we need to make sure that we are including and getting that conversion set up properly.
66 radians. Now I'm going to enter the measured distance that I had with my ruler and do a percent difference. And you can see that in the sample data that I've included as well. Repeat this process for a total of 5 trials. So you want to repeat this 4 more times.
All right, so that's kind of the whole gist of it right there on that one chart. Hang on, I'm going to freeze it. Well, the conversions are happening here. And I think I need to go just a hair bit further because I want to see the part down on the bottom as well.
Enter the measured distance
No,
that
I
I had
wouldn't
with my
play.
ruler, and do apply that in the sample data that I've included
Nope. I know she shows both.
as well.
There we go. That's what I want to stop. All right, so you can see here she measured the distance at 30 centimeters. But then based on the number of rotations or the number of pulses that she receives, or number of pulses, converted to radians, and then we convert the radians into a distance. Okay, so then define the error. And again, she's coming up at 2.4. That's acceptable. If you're coming up over 5, 10%, anything over that, post us your numbers in the discussion or shoot me an email and let me know, because you should never really be getting an error that's more than 5%. Now, in that not the first lab when we took our pictures, but in the second lab when we were doing the distance, if you were up real close to the sensor, you may have gotten some really high errors. But typically, like we're doing here, no, we should definitely be less than 5%.